Okay, today the task is to take a big jump between the spectra of oscillators and the rotational application of basically the same algebra. So we'll be looking at representations that are not these little guys that we've been studying, two by twos and one by ones. But both of these groups that we're looking at, U2 and R3, and the ones that come after this, the higher U groups, all have no limit to the size of the representation. And you kind of see that happening, the fact that we're working with the oscillator algebra in the last thing, which we now are going to extend to two-dimensional oscillator. But the oscillator as is presented in most quantum mechanics books has a bottom, the vacuum, so-called vacuum state. And then there's no limit to the energy states that exist above that. Now, as we know, nature is two-sided. There is indeed, for an electromagnetic application of the two-dimensional oscillator, a ground or a bottom state. But the idea of electromagnetism is that not only do we go up, but we also go down, and all of the ones that have negative frequency, or if you want to be prosaic, go back in time. So we still haven't doubled the size of the two-dimensional oscillator that we're working with here. This is still ignoring relativity, but it does have an infinite extent in the upward direction. So what we need to do is take what we learned in the class 7 here, and we're going on, and work out the commutation algebra. This is, of course, important for all of the ideas that follow from this. Then the idea of crossing the gap, as it were, so that we can understand angular momentum quantum mechanics just from the two-dimensional oscillators. Now, we've already done that classically. We understand now how the rotation groups in 3 dimensions are connected to the unitary two-dimensional complex space. And that was really what we were after when we asked if there was a connection between the two-dimensional Schrodinger equation and the two-dimensional classical oscillator. And this was the Hamiltonian that made that jump. So that's the one that turns out to be the most efficient way to come up with this connection with the, well, basic raising and lowering operators, and oscillators become raising and lowering operators in the three-dimensional rotor thing. Now that was Schwinger's idea. He was first, and Roy Glauber, who won the Nobel Prize for doing that work, and then by that time Schwinger was no longer alive, or he would have been very, very even madder about that overlap. In any case, the idea of coherent states and all of that is really beautiful for one-dimensionals. It's even more so for two, as we'll mention that, but I'm still busy trying to find, or we're going to rebuild applications that do the animations for two-dimensional coherent oscillator. That is connected to the quantum mechanics of molecular rotation. So that is where we're going to get to that order, and then the next lecture on Monday we'll finally do that quantum mechanics of angular momentum in this beautiful way. So let's get started here, because we do have a bit of algebra, and then I want to mention a few things that are connected to this that we'll also be using later on for electronic orbitals and things like that. This particular, and there's our reference frame, this particular ABCD matrix form for a Schrodinger two-state complex equation of motion is connected with, and that is, gives the same equation of motion that you get from this A, B, C, D harmonic oscillator. And the idea of doing, as I say, the lecture, the class 7 was that thick tip pen trick is at work here too. This is the same equation that's written when we did the classical study, but it's thicker now because we're really working with operators now of position and momentum in 2 dimensions. And basically all of the mass factors, square roots of m, the K matrix components, Planck H bar constants, they're being all absorbed into these 4 real variables now that we'll be using. And the other thing that we need to talk about is how do the destruction and creation operators for the 1 dimension that we had when we just had something like that, what do they do when we introduce this other dimension that also has a destruction and creation operator? So there's a little bit of algebra to go before we were happy with that. So we can, of course, just solve for the position and momentum in terms of these magic A's and do the same, exactly the same thing for the 2nd dimension, but it's how they play with each other that's of course going to be important, because here they are living in these weird terms that we needed to make the connection between classical 2-dimensional oscillators and complex, you might say, 2-dimensional oscillators. So that is the real deal here, is what about the commutation relations? And we'll keep these 2 together because I need to compare parts of this with each other. Okay, now the basic idea is that each system dimension is assumed orthogonal. So neither are being constrained by the algebraic or geometrical features that could be there if they weren't orthogonal. And one of them is that the interdimensionality commutativity seems to be the only way to go. So that means that any position or momentum or A1 or creation destruction operator, anything from 1 commutes with anything from 2. So I didn't bother to write that x1 and x2 are going to commute. They commute with each other, no problem. But the fact that the momentums also commute is important. And we'll also find out that whereas if this was both from the first, this commutation is not 0, but we're going to assume that it is. So that's a key part of the thing. That's an axiom that basically is based on trying to do anything else doesn't work very well. But we will get the same commutation relations for these 2 dimensions. That's pretty trivial right there. So, and these are references back to the 1-dimensional lecture 7. Okay, now this for actually n-dimensional oscillator problems will be also taken. In other words, what we do here, we make this step to 2 dimensions. After that, we don't argue about it anymore. And so, no matter how many dimensions you have, this is the rules of algebra for the unitary the unitary m-dimensional group algebra, the fundamental part of it that uses harmonic oscillator destruction and creation. Now, what's really remarkable is, and this is where we need a little bit more than what's written here. We need to expand some of the things that are written here. So I'm going to just take this thing to the algebraic section, which is not something that's been in preceding lectures like this. It's necessary, I think, to see what you get when you do the various combinations, such as A1, A1 dagger, A2, A2 dagger. Okay, these guys right here. Because of those commutation relations that we have there, we get a very simple expression. Namely, we have a harmonic oscillator in one dimension with its 0 point, the vacuum energy there. And we get another one for the second dimension. And that's all well and good. That just is what we calculated with the one dimension situation. But then when you go to ask, what does the x1, x2 product, or the p1, p2 product, or more importantly, the x1, p2 and x2, p1 vectors, or terms that occur right here and here. And so at this point we get to see why it was that this particular Hamiltonian gave us the Schrodinger equation using classical equations, Hamilton's equations. If you expand all of this out, it works very beautifully. So you'll see that, for example, x1, p2, this is the hardest one, minus x2, p1 comes out to be, well, there's one A dagger 1 A2 term with a minus sign on it, and there's another one, A2 dagger A1 with a plus sign on it. And that's taking care of, the minus sign is taking care of the B minus IC. The B minus IC that's right here. So this is the expression which we identified as angular momentum in the 1 and 2 classical dimensions. That is neat. This was the weird one. This is one that where we were used to having a coupling with just with coordinates, and now we've got to have one that has the coupling with the momentum as well in order to play this game.
Dr. Harter, so physically, what does the P1, P2 term mean in your oscillator? Like, does it have a physical significance?
Back in class 4, P1 and P2 were the complex dimensions of a phasor. Right? That was, we had two phasors, one of them involving x1 and p1, then we have another phasor, which is basically the phasor for the quantum wave function. So we already had that before we made this jump here. We already had that before we did this weird sort of symmetrization. And we can see now, just from that algebra, that's exactly what the doctor ordered. In order that we get a Hamiltonian matrix where we replace the bracket that went with 1, 1 and 1, 2 components and 2, 1 and 2, 2 components with these quantities. That's easy to see from this right here. Okay, A1, A1 dagger, A2, A2 dagger. We see that that exists and that this 0 point thing is needed. But aside from that, the off-diagonal components here are just exactly what we would expect. So we're replacing things that don't go anywhere. This is a classical two-dimensional oscillator is just that, and it stays in its little 2 dimensions, never does anything. By putting these connections to creation operators, we get something that can grow infinitely. That is, we'll be producing not just at doublet state, but we'll be producing a triplet, a quadruplet. That's what we're going to get in this development here. And the irreducible representations of any size can come from both this U2 Hamiltonian, but also it's connected to a rotational Hamiltonian very elegantly, just because of these relations, or just because of these axioms, this particular for 1 and 2, and this for any number of dimensions. So this is the step to go further. Schwinger did not, neither Glauber nor Schwinger apparently got any progress in that direction, but now we see that we could make that. I don't know if that helps your question or not.
Don't you rescale the canonical momentum for
Well,
that
we
complex
certainly
part?
did that in order to get
Canonical momentum.
this. Yeah.
Rescale.
Oh,
Yeah.
No, I was just wondering, like, that's that term. I mean, X1, X2 has a that's familiar, but in the Hamiltonian. But P1, P2, I was wondering if it has any specific physical significance.
Besides the
You
product.
see what's weird about this is that in the classical case what we started with,
Right.
it was p squared over 2m,
That's right.
right? And then this was 1/2 k x squared,
Right.
right? That was the good old k, call it the Newton-Hooke equation, okay? Hooke's law, Newton's momentum, right? Newton's dynamics, okay? So all of those things are absorbed in the A, B, C, and D in this symmetrization. So that's why I refer back to this. It's a good idea just to look, you know, I said voila and wrote this thing out in the classical form, right? And I said it was designed to get the Schrödinger equation, right, correctly. That was what it was designed to do. Okay, remember that part? Well, look now, if I make a thick pen, a Hamiltonian, right, that's, I'm meaning now operators, these kind of operators, right, it works. It works to give us a clean two-dimensional quantum oscillator. One that can be stuffed into relativity, because we're talking about electromagnetism when we're talking about a two-dimensional oscillator. We're thinking of just a plane wave coming at us, and the polarization is the vector of motion. Okay, and the waves can be actually going this way and that way. So it makes it for interesting stuff of relativistic significance. Okay. Now, you see, if I was just writing the quantum mechanics of a two-dimensional oscillator, right, my main operator things would be these ket bras, right? Okay. We replace those ket bras with symmetrized, these Mn ket bras with symmetrized A dagger Mn, you see, in this thing. We replace this with this and this, but that just adds up to this, you see. So this over 2 is this plus the 0 point, right, which has got a half in it. That's pretty sneaky. That's a sneaky relation, but it's true because of this algebra. Okay, so that was something that I used to gloss over, but I spent a few hours going, wait a minute, am I really sure about this? And you have to go through this in order to be sure about it. Okay, so I warn you about that. That's something that wasn't in anything I presented before in this theater. Okay, well, let's get busy and use it. This is the same slide as that one there. And the rest of this part right here is just to mention that there's a whole nother area. This is just the half that works with those nice things called photons. But it should be pointed out that we are working with our commutative using something that Bose and Einstein worried about and used as their development of light quanta finally. It took Bose a little bit to do the work that Einstein didn't do on this. And these operators are now called, because of their commutation relationships, boson operators. create or destroy quantum or particles known as bosons. And they have lots of different names to go with it. The one that I hold up right away, of course, is that we're doing electromagnetism of the Maxwell oscillator, you might call the wonderful thing that we call let there be light. Then we've got this guy as a name for what you're doing when you change the quantum number of the oscillator for what are called operator number states. Fox states is actually the name in field theory when you're keeping track of the number of these whatever bosons you happen to be working with. That's called Fox space when you actually are counting well. But we saw that most of the use of light now is a laser coherent state, which is completely washed over all of the different end states into some Poisson distribution and behaves quasi-classically because of the coherence, because of the harmonicity of the quantum oscillator, the electromagnetic oscillator. So we get to play both sides of the streets. And most of the time we're working with light, even the light that we're looking at with right now is quite coherent. Quite a number of different mixtures of Fox states are present in almost every dealing with electromagnetism. It's only when you get very low temperatures and get to the point where you have only a few of these excitations we call photons. But this is true for other things. In crystals, vibrational modes, if you can cool those, you can start playing with individual phonons. So you get the thing here is you take whatever your classical thing is and put on it, right? If you have something called an on, it would be an on-on. If you're dealing with helium-4, the field theory in that is not well developed, but there is a thing called a roton. Okay, rotational, quantum of rotation. Okay, and then of course there's a whole other area where you're working with electrons. There's something that's got an on it, but that's a different beast entirely. That's a completely different thing. Electrons and nucleons all spin a half, and they all are what are called fermions, and they're anti-commuting. So that there you use, instead of the commutator to make your algebra, you use this weird thing called an anti-commutator. And the creation and destruction operators for them, well, they're very restrictive. There's not much they can do. As I say, the Fermi creation operator, and Fermi is the first really to get the algebra going on this, has a very rigid birth control policy. They're just allowed one fermion or else none at all, to state it more clearly. Creating two fermions of the same type is punished by death. There are countries that are almost doing that, but this happens everywhere you have an molecular electronic, atomic electronic, nuclear structure theories, all based on fermions. That's what's in there. And this is without going into quarks or anything like that. This is just what is nuclear physics, atomic molecular physics of electrons is doing. So the death penalty comes because if x equals minus x, then x has to be 0. And that's what you've got here. Okay? So this is, really important idea. So, no two indistinguishable fermions can be in the same state. That's called the Pauli exclusion principle. Pauli worried about this long before the masters got a hold of this. And quantum numbers n0 and n equal 1 are the only ones allowed. As you go through the various states that something called an electron or nucleon can exist. Okay, so we'll come back to this. This is something we have to worry about. And we have to worry about it for the molecule that we're worrying about in this particular course eventually is the C60 here. But C60 with carbon 13 is going to be using that anti-symmetry for all of the symmetry analysis that involves the very finest spectroscopy that we hope to see. Okay, now there's another thing that I want to make sure we go over, and it's something you should already have known. But the usual way to handle two-dimensional or two-particle base states, so-called kets, or the conjugate of that, the bras, okay, which are conjugate kets, and they literally turn the order around. So if 2 is hanging off the end here, 2 will be hanging off the end there after you do the conjugation. That is something that should be discussed. In other words, where did this come from, and what's some of what's behind it, what's going on with whatever algebra you're using. And this is true for bosons and fermions, the stuff that we're doing right here. The eigenstates, also written this way, mixed states, whatever, also written this way. Position states, momentum states, coherent states, whatever queer physics you're doing, this sort of rule applies. And most of the time with light, we're doing those kind of states there for the two polarizations. And scalar product is defined so that they find each other. That is, if I take one of these things right here as the ket side, I say the bra side, and then I have a state right here, then the 2 and the 2 here find each other to make a scalar product. So that sort of arithmetic has to be understood to exist in this weird notation. So we're trying to settle the bookkeeping and the notation for a few slides here, and that's what we wanted them as. And the probability axiom that we hold dear in quantum mechanics has to give the correct probability, Bayesian probability, for these two particles doing whatever state, psi 1 and psi 2, they might be involved in. So this basically is saying that when I take a square of one of these things, it should be finding the probability to have, or to have counted, particle 1 at x1 and at the same instant, or nearly the same instant, particle 2 at x2. So this is a probability to find the particle 1 from state 1 at a count place x1, and this one is the same thing for the second dimension, or polarization if we're talking about light. So the product of these probabilities has to respect Bayesian probability. That is, it's a product. Now, the basic idea then is probability amplitudes that we're talking about here have to become Bayesian. So probability that you two things, probability that would happen is a product. And all these probabilities are less than 1, so the more of these you have, the smaller the number gets. Smaller is the probability that, say, 5 things all happen. It's a product of 5 things. Okay, that's the real behind the scenes of these things. Now, common shorthand I call big bra, big ket. Okay, just show one ket with comma in it indicating the dimensions that, if I was talking about coordinates, but other things can be there too. And then the states themselves, definitely I write that way. And then of course they've got to go through and find each other to make a product.
Dr. Harter, your big bra, big ket is basically a tensor product notation, right?
Yeah. You don't have to draw as many lines and jaggies, right? Dirac is very verbose, and it's much easier just to write a psi and be done with it, right? But in order to track all of the algebra, we use the Dirac now, and that's a way to make it a little easier on you. Okay. Now later on, we're going to talk about Young tableaus as a way to describe the permutational symmetry of all of these things, and that is very elegant and very powerful, but also hard to write. So far, there are no, even math type does not have a place where you can do Young tableau, but we'll get back to that later. Now, the other thing that is got to come up here is when we do this stuff, we have to ask, how are these structures stored in a computer program? How do you, what's the best way to put them down? Well, there are many ways. And the usual answer is you make tensor arrays. Store these things as tensors. So that's what we have to discuss. And I'm going to go ahead and bring this computer up to speed here so that we can make some comparisons here. And this is the first one I need to do. So if you start with an elementary ket basis for each dimension, say you have a state 0 that something can be in. This is type 1 particle. Say this is photon for X polarizations that we're talking about here, and this is for the Y polarizations. You have a possibility to be in this state, or this state, or this state. These are all the unit kets that go with those possibilities. But at some point, even though this goes to infinity, you got to stop somewhere. So you stop and say, hey, I got to worry about the other dimension, and you go blah 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 blah, and you got to stop it somewhere, okay? And you're limited by the finitude of the computer that is going to be storing in the information. So what you're really limited to, if you're going to talk about two products, is the various outer products that you would be making to keep track of in the in whatever computer you're using. So it's at this point that we take the Kronecker product of the things that have to do with type 2, that's say Y polarization, and type 1, the X polarization of a system that can have an infinite number of photon excitation possibilities. And we're fortunately, because of that beautiful coherent state and the harmonicity of the harmonic oscillator, not having to go very far before we, can make a pretty reasonable theory out of this. But you do have to go ahead and have a ket that looks like this, and then another ket 0, 1 that looks like this, okay, and another one is 1, 0, okay, looks like this. You see how they place the numbers in these things in order to think. Now, as I say, this is a conflict between standard infinite dimensional analysis and the finitude of computers, okay? And basically what it boils down to, very often, is you make adjustable size phasor arrays, and then you just, you work your theory. The convergence is achieved by, as I say, orderly upgrades in the number of phasors. In other words, you use more and more memory, and you see where is that point where the results do not change. And if you're talking about coherent states, there's that tail, and the idea is that you find how far out from the tail you can go, where your results don't change if you increase the dimensions. Now, if you excite the thing more heavily, then all of a sudden you're going to have to use more memory because that Poisson distribution starts to get bigger. But as long as you can be guaranteed that there's a limit to how much space these things are going to take, that there is a point where you say, I think I've got the right answer now to a certain degree of accuracy. I don't have to go any further in grabbing memory to run this simulation or whatever it is you're doing. So you see there's a lexicographic sort of numbering system. Array indexing is called. Very not too different from what you have on an odometer in a car that counts hours thing. The first thing you do is usually on the right, you increase that number, that's the least significant digit, and then the second one here gets increased, and you go through the first again, and then you increase the big one, as it were, and then you go through with the little one. Okay, and there's a name for this funny thing. It's called Little Indian. This is computer terminology that probably is considered politically incorrect now, but it's because there's this little song called The Little Indian, and the indexing is here. There's also Big Indian that does just the opposite, anti-lexicographic, where the thing on the left is the least significant, and the end, the right-hand side, is the big guy. This is the Big Indian indexing. So most significant digit at the right end is this one. This one is often used as well. And then the notation to use for the outer products of the general case where we're asking for what's the amplitude of our wave function psi 1 for all of the quantum levels, 0, vacuum, 1, fundamental, 2, overtone, blah, 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 blah. And we want to do that for the other polarization if we're talking about light. That's what we're going to have. And then you array these things similarly to this here. So this takes getting used to, particularly. You get more used to it when you actually are having to program things like this. So I thought it would be worth our time to make sure you have at least thought about this, to get an idea. It is not trivial at all. And the question is, are there better ways to do this? We always are looking for that too. But so far this is the best we've got, even with our powerful computers. Now, shorthand, again, big bra, big cat. Okay, so here I just go and I say, okay, particle 1 or dimension 1, and then I read off its values in these the bra side of it, and then the psi, whatever that is over here on the right, making a scalar product with each of those, and that's the way you describe the state psi. Okay, and then you can shorthand that to this. Okay, so. And that would be a little Indian. The least significant digit is on the end, the right end. That's usually what we do. Okay? All right. Now, this is something else that I've always wanted to do something about, but I just throw it out as a moment here. We're putting these products as our states, but remember when we did products ket to bra, or I should say bra to ket, we're making the operator components, okay? This guy right here is called an nilpotent operator, because if those are orthogonal states, you multiply that guy by itself, you get 0, because 1 and 2 are orthogonal. 1 and 1, of course, the same states, they're normal, so that particular operator right there, you multiply it by itself, it comes back itself. We've already seen those as projection operators. We've got to also worry about these projection operators, and we will be doing that fairly shortly here. But if you take a two-particle state, say one that's being described by bras, and you have one-particle states that make up the product, okay? And as I say, those are very common. These are less common, the ones where they're actually equal, in equal states. Bosons like to do that though, so it's not as uncommon as you might expect. But anyway, I'm making an analogy here between an n by n matrix operator that's a combination of these things, okay? And of course, if you diagonalize that thing, if you use a basis in which this particular matrix is in using its eigenbases, okay, might be diagonalized, so it's just a sum over where those guys are equal. Okay. Well, isn't there a generalization of that we should always be looking at? These are entangled products. This is very entangled. We've got its coefficients for all possible combinations, presumably, to make that state. So that's an entangled state, very entangled if all those coefficients are non-zero. Do we gain anything by looking for the equivalent of eigenvector projectors for a two-product state? Just a thought, okay, just something to think about. All right, now let's get, we got to get busy with what's at hand here. And that is making the jump between the general set of oscillator relations that we're going to have for two dimensions. And they're basically the same as the relations we had just for one. This is one dimension over here with the relations that are written up on the wall there. I forget where they are actually right now, but if we look right here, these are the general connection relations for states and operators. We got one dimension and then the second dimension, okay? And the deal is that when an operator comes up on a product like this, it finds its type. Now, A2 comes up here and it looks like it's going to run into A1. But that's not what you're supposed to be thinking about. You're supposed to be thinking about that this A2 here just does not see that thing at all. It just goes right through it to its own kind. And then the A2 here, it's this thing, you see. And at first it looks like it's going to do something to this, but it doesn't. It goes right through to this one. And then it gives the relations that we know. The Feynman mnemonic applies at this point. This is a destruction operator of quanta. It will produce N2 minus 1. It will not touch N1. That's the idea of the orthogonality. Does that make sense? And you use the square root of the larger number involved with 2. Okay? Which is N2. This is smaller. So I don't use that. But up here, when I applied the creation operator, I raised it to a larger number, and that's the one that shows up in the square root. And 1 is not involved in this particular case, where I was working with a operator from the second dimension. For the first dimension, it kind of happens the way you'd expect. This runs into N1 right away, gives you that. This one runs in there, drops the thing by 1, and gives you that. So these are all the matrix elements we need in order to produce the entire theory of quantum theory of angular momentum, which is the goal here. That's all we need. And that was the elegance of the Glauber Schwinger thing. That's what they realized that, hey, we can make use of oscillators. But it's also important to realize the physics behind that. It's basically saying that that's all an electromagnetic field is a collection of oscillators. And oscillators are simple. We should be able to get our minds around all the weird phenomena that has to do with light. As long as I can just play with this stuff, it's definitely the case. Okay, so here is the base state for a 2D oscillator. You start with a vacuum in the x direction, a vacuum in the y direction. And you apply any number of creation operators to that. And we know how to normalize it. If it was only one dimension, we divide by square root of the factorial for the quanta that we have chosen here, and then this one just does the same. So that's the formula we need, along with these, to get the quantum theory of angular momentum. But also all of the stuff that happens with two-dimensional oscillator, which is on a completely different physical plane, so to speak. Okay? Now, these combinations in this Hamiltonian, namely that Hamiltonian right there, that's the Hamiltonian that's going to take us to the angular
Dr.
momentum
Harter, just a
problem.
quick question.
Yes.
So, Schwinger showed that you can develop the theory of angular momentum using 2D harmonic oscillator.
That's
that's
it
what.
right there.
But is there any such correspondence between 3D harmonic oscillators and quantum theory of
There,
any correspondence between three-dimensional oscillator algebra?
yeah, in other words, what is it that would map onto a three-dimensional oscillator that we work? Well, there's a famous Nobel Prize for one of those, the U3, right, of high energy physics,
Okay.
right? The quark model, Gell-Mann,
Okay.
Zweig, Neyman, there are a bunch of people that actually, Gell-Mann's not the only guy. I actually worked for George Zweig as a TA, wonderful, brilliant guy. I really couldn't get along very well with Gell-Mann, but Zweig, he was just kind of like Feynman, and got along with both of those. He invented the aces, 3 aces, but he didn't really know a lot of group theory, neither did Gell-Mann. The guy I finished with, Bill Wagner, just loved group theory from the first time he saw it, kind of like I did. And it was when I finally solved a problem with group theory that Feynman couldn't understand, but he still said it's really neat. He says, you ought to go see Bill Wagner. So Bill Wagner was reading a group theory book in 1960. It's got Hammermesh, the book that you brought in here the other day.
Classic.
Okay, that he was, about halfway through that thing, and in walks Gell-Mann, just wandering down the hall, and he sees Bill, and Bill had gotten his PhD with him. He says, what you reading, Bill? And holds it up. Hey, let me see that. Group theory? He said, you'll never do anything with that. Well, a year later, he goes to Israel. He's interested in seeing just the fact that it's a Jewish state that's newly founded, right, at this time. It's having its problems, as it is still today. But he goes to Hebrew University, and there's Julio Rocca as the big guy there. The guy does Rocca coefficients. We'll be talking about those later. And Rocca gives a wonderful course in Lie algebras and groups, which included U3. The rest is history. He started then figuring out how the irreducible representations of U3 would take up the various nucleon resonances that were coming out of the very highest energy accelerators at the time.
But is there a mapping between U3 and any problem in non-relativistic quantum mechanics?
Yes, there is, and that's what I emphasize, is you don't have to go to high energies to see a wonderful application of U3. Just do the atomic P shell, which we'll do later. The atomic P shell, P means angular momentum 1. Just fill it up and categorize it by representations of U3 using Young tableau, and that's where the power of the Young tableau will first be realized. I don't know if that answers your question, but there are other things that U3 does. Basically, any quantum mechanical system of 3 dimensions. Okay, anything else? We should keep going here.
Yeah, one last problem. Angular momentum, the theory of angular momentum is a 3-dimensional problem. So so we deal with Jx, Jy, and Jz.
Yes, it's this guy right here.
Yeah. Yeah, but for whatever reason, we are able to map that problem with a 2D harmonic oscillator.
Yes.
So what is the essence? What is that key feature that enables us to use a 2D harmonic oscillator algebra to develop a 3-dimensional problem, which is...
I think we'll answer that by the end of this. Yes. Basically, commutation relations. Because that's the underlying multiplicative structure that we use in dealing with these things, which we'll tackle. Okay, and then we'll tackle it some more, and we actually get this on Monday. So, yeah, no, that's a good question, and we'll try to answer it quickly. Okay, so here's what you've got if you're dealing with a two-dimensional oscillator. You've got the vacuum first, okay? And I'm doing lexicographic little endian indexing here, okay? So I'm imagining this matrix that I'm going to have in my computer, and I'm going to lay out the base states as a first shot here using that lexicographic stuff. Now, since I want to compare this with itself quite a bit, I want to bring this screen so it is in cahoots with what we're doing here. So there are the two identical slides for this particular page. So what do we got here? At first it looks really complicated and really nebulous, and I've sort of covered up what we would get if we looked at all of these. But just for the moment, what do I got here? I've got the vacuum for polarization 1 and the vacuum for polarization 2, if this were the two-dimensional oscillator, N1 and N2. Then I just go ahead and I start loading up the little endian. I start saying, okay, polarization 2 now has one quanta in it, but I've still got polarization 1 at the vacuum, 0. And then I just keep going right here like we were saying we should do with our Kronecker products. So I go 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, as far as I need to go to count for all the quanta that I'm going to have it going in this model. And that's the dot, dot, dot ellipsis right there, okay? And then I say, all right, polarization 1, now you can have one quantum, okay? And then I go 0, 1, 2, 3, 4, 5, 6, 7, 8 with polarization 2. Or particle 2, if we're talking about two particles here, okay? And then finally I say, okay, number 1, now's your chance to have two quanta. You see, now I got to go through 0, 1, 2, and 3, and 4, the second quantum, okay? That's your first cut right there of making a matrix that the computer's going to diagonalize, right, to find eigenstates for this thing. So I've got the same set of states lined up on this side. These are the bras now, and those are the cats that make this matrix, okay? And presumably, no problem, I just get my Hamiltonian, which is linear combinations of 1, 1, 1, 2, 2, 1, and 2, 2, and there's a matrix element sitting right there that I need to plunk down here for each of the components of this Hamiltonian. You see, I've got this operator here, I've got this operator right here, and this operator here. The diagonal operators have this extra vacuum term, but aside from that, we're just loading up matrix L numbers for this very nebulous, very open sort of matrix. Okay, so it's not a difficult thing to just write down what you get from each of these things. Now I've taken the 0 point stuff and just taken it outside. Presumably you're not going to have to worry about that. That's kind of like the part of the phase problem that we throw away. But to once again remind you that we might be doing some information theory here, we do not throw away that. That's very important. So, you know, if you've got to worry about phase, you can't throw that away, or you're in trouble. So, but all of these guys here actually have numbers that are given by these matrix elements, and it's, this one goes forever, this one goes forever, this one goes forever, but it's got to stop somewhere. So there will be a highest, say 2. That's if that were the case, what would we have? Okay, so the deal, of course, is that now you get to see kind of more of the matrix, and it's just growing and growing and getting extra factors there from these numbers. That is something you should should be able to visualize at this point. Okay, for this particular Hamiltonian, A, B, C and D are the parameters.
Dr. Harter?
But there's a trick now that we need to do, but let me
Yeah.
answer your question.
Yeah, so if you set B and C to be 0, then obviously this Hamiltonian is diagonal. Where
If B and
if
C-
is 0, it's
If this is 0,
then it's a decoupled
It's just
two-dimensional
numbers.
oscillator. Yeah, no.
just a number of operators. Wouldn't it be nice if that's all we had to do?
Yeah, but in this
Right.
case, this matrix is not diagonal in this basis. So
Right. It's mostly zeros.
yeah, but still,
Right.
you still yeah.
All of this stuff here, the little dots, there's nothing off of this super diagonal. There's nothing off of this
That's
super
right.
diagonal, you see.
But is there
But we can clean this up in a very important way, and that's what we have to do next. Okay? So, let me put on this screen the picture of the unfinished matrix, and then we're going to go for the one that's a little bit. It's just a rearrangement, a very obvious rearrangement that we're going to be doing. Here I'm just showing you a couple of the matrix elements, so I might skip this one if you don't have a question about it, but basically I'm just showing where I got the square root of 2, okay, for this one, and similarly for the other ones. And it is a Hermitian matrix, so whatever I get should be that. In other words, this guy should match that guy, this guy should match that guy, and you see it matches by turning the I to minus I in order to be Hermitian and all that. Okay, but here's the rearrangement. We're going to rearrange these to a block diagonal form. We're going to get the base stats with the same total quantum number in a block. Very different from just doing the little Indian stuff. We're going to make a smarter arrangement here. So, if I only got one quanta total, I only have 2 states. I just reproduce right here. If it's 0, 1, 1, 0, I just reproduce here what we call the fundamental vibrational subspace. So, right here you will see, apart from the 0 point stuff, you will see almost a copy of the original matrix A, B minus IC, and B plus IC. Now, this particular one is done in such a way that you should see that if I do this thing lexicographically, then I get the plus IC up here and the minus IC down here. But aside from that, this is the same matrix that we were solving just to do the classical two-dimensional oscillator. And at that point, we were doing quantum mechanics as well for the fundamental of this two-dimensional oscillator, namely the states that are just combinations of 0, 1 and 1, 0. Now, when we do the vibrational structure of a molecule or something like that that has 2 degrees of freedom that are degenerate, well, our fundamental, it's called the E usually, fundamental, okay, is just going to have 1 quanta in that, 1 quantum of vibration in that. Or if it's in a solid state physics, the band that's associated with that 1 phonon, you see, is going to be doubly degenerate, and we're going to be able to think about it classically. We'll use classical mechanics to discuss the dynamics of a vibrational mode that is in the fundamental state with 1 phonon. That's kind of cheating, isn't it? And that's the way physics is. Almost all of our field theory, you do the classical stuff first, and then you just sort of add the quantum mechanics as window dressing. You get to do that because it's fundamental. Or maybe just 1 excitation from the fundamental, where I've got 2 quanta. Here are all the ways that you can make 2 quanta total out of these lexicographic states. Obviously, 0, 2, okay? And it's flipped, 2, 0. But there's also 1, 1. In each of those cases, the numbers add up to 2, okay? So, this block right here, and there's part of it right there, that's where the square root of 2 we were talking about before comes. But this is overtone, the first overtone. I just call it the overtone 2, vibrational subspace. Okay? Now, in the angular momentum theory, this is going to be our angular momentum 1 state with 1, 0, minus 1 for a p shell, okay, a p orbital, okay, or a p rotor, a rotor with 3 substates, total quantum 1. Here, it's total quantum 2. Remember, there's going to be a 2 to 1 between these guys, and that's where it comes as far as quantum counting. What's the next stop? 3. Okay, how many ways can you make 3? Well, it turns out there's 4 ways to do that. 0, 3, 1 plus 2, or 2 plus 1, and 3 plus 0. Okay? 4. Where's that in angular momentum theory? That's 3/2 angular momentum. This is 1/2 angular momentum. Right? So here we're putting all together in one place, not just a quantum theory of rotor angular momentum, which would be 0 and 1, and then down here is a great big 5x5 matrix that accounts for angular momentum 2. But in between that is 1/2 and 3/2. Okay, so I want you, to see how it happens. This is where you see what the connection becomes between quantum theory of rotation or orbiting in an atom, okay, and the quantum theory of the two-dimensional oscillator, which is what this is on the face of it. Okay? So there's your overtone 3 if you're talking about vibrations. That's 4 states. Okay? And it's a very undiagonal matrix, but it's got a lot of zeros up here and a lot of zeros up here, so it's begging to be diagonalized. And of course, that's what we're really after when we're doing these things. So here's a formula for the eigenvalues. If I only had A and D like you were talking about, okay, then I wouldn't have any of the B and C stuff, right? The bilateral and the curly complex or whatever, if it's out of here, I'm just looking down the diagonal here. And so there's a formula for the diagonal case right there. We don't have to go any further with that. And the idea, of course, is to use that formula later on. So, the way you make it so that you're always using that formula is to simply diagonalize the fundamental. That's our ABC matrix, right? If we diagonalize that, and we know how to do that with all that funny stuff with the cranks and the spin vector, right? We should be able to go ahead and write a closed form analytic expression for any of the quantum matrices that you've been seeing there. Okay, so let's take a look. There's the thing that we were just discussing. I want to go ahead a little bit here. So, recall the decomposition. The decomposition of H. This is back in class 4, page 16. This is a link, I think, that may or may not work. We are in the middle of changing from a very old computer that is sitting there with sulfurous fumes coming out of it, and who knows what is wrong with it that they have to replace it, but they do. Mainly they want a bigger and faster one, right? So we'll be sitting on a bigger and faster computer with all of this stuff, and supposedly it should be without much effort on your part. That is, we've got to change all the names of everything we've ever done a little bit in order to make sure that we use the newer computer, because it's going to be turned off on March 10th or something like that. So we got to get that. That's what's happening right now. So this link here is either to one or the other. Right now there's 2 ways to address.
Go ahead and kick it off and we'll see the URL, because then they'll know whether they're on the new system or not just by looking at it.
This one right here, I could just back out of here and show that. Or I could go
Just show it in the address bar.
Yeah, let's go ahead and do that. We've got time.
Oh.
So it sent it to that. Okay, that's going back now to class 4. We're working in Chrome now. If you work in Chrome, you don't get thumbnails. If you work in Safari, you don't get thumbnails. Only Foxfire. If you want to work in Foxfire, you get thumbnails for the whole lecture, and that's, I think, people are used to using that. Anyway, here's the address up here. And as you can see, that's an old-fashioned address, right? There's UA here, and mod phys, and then a whole bunch of stuff to, you know, designate this particular thing, including the page number, which is at the very end of the URL. Okay, so be aware of that. I presume I can just go ahead and scroll down there. There you go. There's page equals 16. Okay, that's the particular class 4 date that was done. All right, and then this is all the stuff that you need. From here to here will change. And we'll talk about that later.
Yeah.
Okay, but that's what we need to know about, just so you're aware. If something doesn't work, give one of us a call or an email. We'll tell you.
Call me
TC
first.
will be the one most certain to know about it, but I may already know it too. So I'm slowly learning all this. Okay, so anyway, here's the expansion of this matrix the way we did it when we were talking about classical mechanics of 2 dimensions of oscillators. Well, this is the fundamental, so it's the same sort of discussion. But in terms of these spin operators, we're going to be able to crank up these spin operators, and they're going to have commutation relations and all kinds of stuff that's going to come out of the commutation relations of the A's and the A daggers. That's where we're headed. Okay, that's what we need to complete today. I think we've got time to do that slowly. And anyway, the frequency eigenvalues, if you recall, are found by making sure that the spin vector lines up with the crank vector. Okay, so that means that you better use the Euler angles of a state, or set the Euler angles of the state to the values that the crank's polar angle and azimuthal angle has. You see, so again, this is class 5, page 72, and I don't think that one even has a reference at this point. But we're going to try to make sure that it does have one that will work. So that's the deal, is that the Eigen creation operators, this is the most important part, because this is what lets you do it for any of the high quanta that you would have in the actual quantum model. We're going to have a plus creation operator, we're going to have an A minus creation operator, which is simply made out of that crazy thing combination. In this case with a plus sign, in this case with a minus sign. That's all the difference there is. The polar angle goes up by 180 degrees, and so that makes this into that. And then this thing right here, the sine of theta over 2 goes to a cosine. Okay? So you get an extra plus and minus sign, and then you get the transfer of a cosine into a minus sign and a sine into a plus cosine. Okay? So those are the two, shall we call them, up and down states, plus and minus states of these that these vectors show you here. Okay, this has got the minus on the sign right here, and this one has got the cosine right here. This is the reverse. Cosine's up here, and the plus sign is down here. Okay, so we're just rewriting this thing using these components, but the basis vectors are creation operators for the 2 dimensions. Then there's the overall phase, which we don't want to forget. It's part of the story these days. So we're going to get the H eigenstates directly from this. There'll be these two guys that are the eigenvectors that we're talking about here, omega plus and omega minus. Those are the creation operators that go with them. And we need that. Anyway, this is what it comes out to be. Remember when it was always just written as in terms of A's and D's? Well, now the A's and D's are omega plus and omega minus. We're in the eigenbasis of the original fundamental. So there's the answers. It's really simple. Okay. And you're kind of seeing the angular momentum structure here. Divide by 2, 1. It's a little bit screwy as far as that goes, but it's a very simple arithmetic that's giving us those answers. Okay, so this is that formula again, but now A and G are omega plus and omega minus. Now here's another way to write that. We just keep writing this thing in different ways. We can collect the omega part under a difference between N1 and N2. And then we've got a total N1 plus N2. Those are the important arithmetic things. Now just remember what this is. This is the vacuum block. This is the fundamental block. This is the first excited or overtone block, the 2 block, then the 3 block, and then the 4 block. That's all you're going to get with this thing and its form. You pick the right combinations for the eigenvectors, that you will be getting a closed form formula for this thing. Now here, for the first time, are the quantum numbers that we'll use for the angular momentum theory. J for Jordan, and M for, I don't know, but magnetic quantum numbers, where that comes from. Magnetic remote number, okay? This one is half the sum of the 2 quantum numbers that sit in the formula and the sum there. The asymmetry quantum number, I guess, is the best way to write the M, because it's the difference between those 2 quantum numbers over 2. So simple sum, half sum, and then
this is a definition, right? You're defining your J and M to be this way.
Yes.
Okay.
Yes, absolutely. Defining it here.
And also, so
this sum here is that, but that's twice this one. Yeah.
So we diagonalize this matrix by setting B and C to be 0, right? So basically we just had A and D in the Hamiltonian.
Well, in a different frame, you see, and that's what you find by doing the funny stuff with the lining the crank up to the state vector, right? Once you've done that, B and C are out of here. And so you only have the first diagonal and the second diagonal, right? And the difference between those is A minus D. Then you've got an A plus D that's making your phase, right? Does that answer what you're after right there? And then we go on and say, hey, it works for the subquantum number M here. And this is the picture of it, okay, right here. The omega sum, the thing that has omega 0 that drives the phase, is this omega right here from 0. Okay? And then this is a nu equal 1 state that makes the 2 states that we showed pictures of. And this is the beat frequency, omega. So omega plus is that omega 0 plus the beat frequency times 1/2, or minus 1/2. You get 2 states. Spin up, spin down if you're thinking spins, but now we're maybe not. This could be a part of something that had a different physical interpretation. Does this make sense? Okay. So we're sort of getting in like Flynn here with the connection that this provides. This whole deal here, omega plus and minus written in terms of A, B, C, and D is here, but we just go ahead and go to the place where the B and C are 0.
Dr. Harter?
Yes.
Where is all of these in the book? What chapter specific?
Oh, you're talking about the QTCA, quantum theory,
Chapter 7.
computer age?
Chapter 7. Unit 7, I'm sorry, on harmonic oscillator.
Yeah, it's under the harmonic oscillator unit.
Yeah, I can tell you exactly one second.
Yeah, which is, yeah, thank you, because I didn't remember the chapter offhand.
Unit 7, chapter 21.
Great.
21, 22. I mean 21, yeah.
Yeah, unit 7, chapter 21.
Okay.
Not chapter 7.
At the top of the info page, there's a link to an exploded detail view, almost a table of contents of the TC.
Yeah, go to the web version of it, and you'll see all of the chapters, units
Okay.
listed, right? Click on the, there's a table of contents, basically, is what it is, a description of the units.
Okay.
Yeah. And the same goes for lectures. They also,
Oh yeah, I read the lectures, but I like
the textbook has an advantage of,
it has the words like I'm looking for like those words that say, oh, this makes sense.
Yeah.
Yes.
no,
Good. That's
you're
feedback
exactly
I need.
right. Books aren't dead yet.
Yeah.
They're just covered with silicon.
Books aren't burned yet.
Yeah, books aren't burned yet. If they're made of silicon, it's a lot harder to burn them. Right? You need a lot of temperature before sand burns.
Yeah.
So we got some time left yet. Okay, sorry about that. All right, now, just to give you another sketch of what that means, is you're just talking about SU2 multiplets, and you always wanted to have them be spinners, that is a halves, always be anti-symmetric. If that's what your thing was, well, there's a half, and then there's 3 halves, and this is the half, and there's the 3 halves right here. But it's 4 states, 3 halves, 1 half, minus a half, and minus 3 halves. But of course the doublet, you know that is spin a half and minus a half, right? But they fit right in between the guys that you're going to see if you do R3. If you do R3, you don't play with these necessarily. You just work with integral angular momentum of, say, an orbit of an electron. So this would be the s orbital, S for, forget what S stands for.
Sharp?
Pardon?
Sharp.
Sharp. The sharp lines that come off of the S in the Balmer spectrum, I think, is where that comes from. Okay? So S stands for sharp. Well, that doesn't help you much, does it? Okay? And then P, principle. There was and I'm not really clear on this, but the P lines are apparently called principle because they stack up nicely and then they're all bright, or something like that. Yeah, they have roughly things. And let's see, what's D? D is diffuse. That's this guy, D states, right? Or angular momentum 2. And apparently the Balmer series for the D is really hard to see. It's fuzzy. But they didn't use F for fuzzy. They used F for fine, which is the 3 that's not drawn here, right? So there's all this nomenclature. It comes from spectroscopy. We had absolutely no idea where this light was coming from, right? And we don't put letters on these guys. But anyway, when you put them together, look what they do. This is, you know, by using this formula and plotting the splittings as a function of omega, okay, that's our one parameter really that designates the splitting. You'll see that right at 2/3 of the little omega, they all come back together again, sort of. But they also do a little bit of getting back together right here, okay, and then right here, and so forth. So this is not too different from some of the coincidences that occur in that space-time thing that we showed of the revivals. There's a similar sort of number theory going on here, which is highly amusing, and I apologize for not exploring it more. It's just one of those things.
Just
that
don't
needs to
fold it
look.
back around.
Now, just to get you used to the notation and the nomenclature, we are talking about the spinor states, and we do write them this way. We write J in the top part, and we write the M value, the half difference between N1 and N2 over 2. We write that in the lower portion here. So these are all states that are labeled by a J on top and an M underneath, and that will make sense as a good way to do things. So here's the J value, N1 plus N2 over 2, and there's the M value. And let me bring this, let me bring this computer up to speed here as well. Well, I'll stop right there because that's where these formulas are shown. And then there's this guy right here. Just invert this. N1, the thing that we talked about in the harmonic oscillator, or N2, the two quantum numbers of the 2D guy. One of them is J plus M, the other is J minus M. J being 2 nu, and M being the magnetic or mode number quantum. So talking about J equal 2, the tensor, this is the vector, but these have different names. The 4 spinor, this would be something that would make a U4 structure. This would make a U5 structure, so the unitary group can jump in at any point here. U3, I already mentioned, takes care of the angular minimum 1, so-called P shell. We'll be doing that one and that one a little later. Using, and here's an elementary application of the Young tableau. This is the way you would draw a Young tableau state for, say, 2, 0, 1, 1, okay? By these conversion formulas here, the 1, 1 right here is associated with an M value of -1, 1, 2 associated with 0, and then 2, 2 associated with +1. That's just a particular choice of naming this one 1, spin up, +0.5, this one spin down, -0.5. And the boxes in a row represent that they're totally symmetric in all of these states. Harmonic oscillator states are bosons, so no argument there. Bosons are totally symmetric, so that's the kind of Young tableau I would use if I was going to lay them out in a quantum diagram like that. So the real vacuum is here, the fundamental is here, the first overtone here, etc., that we've been talking about using what's more common nomenclature: spinor, 3-vector, 4-spinor, tensor. They kind of run out of names as you go to higher and higher rank of the tensors that live at J equal 3, J equal 4, and so forth. Okay, so this is stuff we're going to be doing in detail in the next lecture that does angular momentum, wave functions, and all of that stuff. But we have enough time here, I think, to get a nasty part of this out of the way, and that's the commutation relations of these raising and lowering operators that you will be using for R3 and O3, the rotors and the orbiters, and all of the stuff that goes on in 3 space involves a different kind of raising and lowering operator than the A's and the A daggers. So that's something to do here. But I would like you to see this before we go on, and that is, you've already asked me about what would U3 offer you, what would U4 offer you. Well, if this is the dimension of the oscillator, we started with 1, right, which is so much less structure than all of this other stuff, okay? Then we today quantized the n equal 2. And when we did that quantization, we discovered that the ground state, the fundamental, the second fundamental, and so forth, was a little bit more complicated than it was for a one-dimensional oscillator. With a one-dimensional oscillator, all of the excited states are one-dimensional. Big deal, right? But for the n equal 2 oscillator, okay, that's a little bit more common. First one is definitely 1. Ground state vacuum, that's always 1, okay? But for the next quanta, you see, it's 2. And then the next one after that, the number of states is 3. Then 4, that's the force spinner. And then there's 5, that's the angular momentum 2, okay? And then there's going to be 6, 7, 8, 9. So always the excitation number determines the degeneracy if you're talking about two-dimensional oscillator, okay? Now go to the three-dimensional one, U3. What's U3 offer? It offers a vacuum state. It offers, right off the bat, the fundamental is the dimension of the oscillator, okay, 3. That's the quarks for Gelman and Niemann and I've forgotten the names now, George's name, I can't think of George's name, I'll get it later. Then there's the, what they call the biquark, which doesn't really show up very well on the accelerator, but then there's the rank, the 10, the so-called decapulate. That's what got Nobel Prize for Gelman. And then there are more excited states that people have had a hard time filling. So, unlike atomic and molecular structure, which uses all of these things for anything that involves 3 states, high energy physics is very picky. And then the next stop would be, say, 4-dimensional oscillator. Okay, wow, those number degeneracies go up pretty fast, and you can see 5 and 6. They're going to be big. They're just triangular numbers. They're the binomial coefficients in a Pascal's triangle. Okay. This one is just putting cannonballs in a line. This is putting cannonballs in an array, like billiard balls on a table. This is actually like cannonballs in the Civil War monuments. And then I can't draw past that. It's 4-dimensional. Okay? So this is the geometry and the algebra of just the dimensions and the quantum number of oscillators, harmonic oscillators. And just to give you an idea of what 3 looks like for the bosonic symmetric states. There's the little quark guys down there. There's the biquark right there with 2 quarks doing something, but apparently not very well because they're hard to find. And then comes this guy right here. Okay, you're talking about 4 states here, 3 is 7. Plus 3 more is 10, the decapulate. So that's the one that won the Nobel Prize right there in high energy physics, and got the quark model to be believed. And this is a 3-dimensional drawing. Now 4 dimensions, it's hard to draw that, but there are ways to do that. Now it wouldn't hurt if I had an animation of these to play it, but I don't. I've been looking around. I had all of this stuff on graphing calculator, and I could make these things oscillate. I could make this one do a little dance that was like the beating motion that we saw when we did the orbits. And what we would really like to see is a animation that could make a coherent state in 2 dimensions. And basically what that would pretty much be, although not quite that simple, but it would just basically be a big spike going around a phaser in a circle. And it could go either way. Depends on how you set the initial conditions. Anyway, here are the actual wave functions for this thing here. We're talking about a 0-0 state, that's just a Gaussian. Then here's a 1-0, and here's a 0-1, okay? This one is plus and minus this way, and this one is plus and minus this way. Then this one is a combination of a 1-0 and a 0-1. It makes a thing here that oscillates very fun. If you split these two, the energies, if you don't, it just sits there. And this one is a similar arrangement of combination. of 1, 0, and 0, 1. In other words, these two. Okay, so if there's a splitting between these two, then those move. If they don't, they don't.
So you said there was a classical quantum correspondence for the 2D harmonic oscillator?
Just as there is for the 1D, a coherent state, right? In other words, all you have to do is make a Poisson distribution, basically. But you can boost and punch in any direction, right? Best way to do it is translate first in the X direction of polarization, then in the Y direction of polarization, right? And that's the thing I didn't point out, was that all of those coherent states that we looked at yesterday, I might as well get it started again because it is so extremely beautiful. All of those coherent states are made by translating the ground state. That wave form there, and that's the thing I neglected to mention, that wave form there is the form of the ground state. The Gaussian that you calculate first for n equals 0. Right? Now we have n equal alpha. What alpha means is there's a whole bunch of n's, right? And you can see the combinations there that were taken there. And this is the thing that you're going to have on the program presumably. So you can blow up the phasors and see all of these phasors are moving a little bit. These guys up here, you can't even see the motion, but you only need 1, 2, 3, 4, 5, 6, 7 oscillator states to make a pretty good Gaussian. Moving Gaussian, right? That's the ground state in motion. Ground wave in motion. Well, the same thing is going to happen with this. The ground state, this thing, will just be off-center, and then depending on what other parameters you go, you can either make it dissipate or you can just make it go around in a circle. You can make it do all of the things that the classical two-dimensional oscillator could do. With all those funny orbits, you can make it do that. But you can also make it just dance all over the plane. I mean, that's a very special thing there, but if I just go and change any one of those things to something else, like I just take this one and change its phase, go by Gaussian, right? I just changed one of them a little bit. So the coherent state is a fairly delicate fellow in that sense. But usually you don't have such easy control over those phasors, right? In that sense, it's quite robust. And lasers wouldn't work if it wasn't. Okay, let's zoom ahead here just a bit here, because what I want you to see is that this combination can be rewritten in terms of operators that we call spin operators back in the classical Stokes thing. And this is just a look at the expansion that you will get that's analogous to the ABCD expansion of the spinners. There's B, it's actually B over 2, because I've got 2B out here. This is A minus D over 2 times 2. There's the spin a half, that's the actual spin operator's SZ. This is SY, that's sigma Y over 2. Here's sigma X, that's our sigma B over 2, okay? Well, you go up to the next excited state. This is the fundamental. You go up to the first overtone, and you get these matrices from our calculation that we've just done. And if you put them in the right places, okay? And then let's go for J equals 3/2. This is the 4x4, okay? That's the matrix it comes from. There's how it expands out. All of these things are 4 terms, counting the unit matrix. And then 3, the spin operators. that are now being represented by what will be our irreducible representations of angular momentum. So we've already done angular momentum calculations here up to that quanta. So we're looking in general for a given J, that's 2 times J is equal to the total oscillator quanta. J itself is going to have a degeneracy 2J plus 1. And that should be a familiar formula, but it will be certainly familiar by the time we get done with the discussion of this, particularly next week. But the idea is these are all J blocks now, 2J plus 1 dimensional blocks. And that's what this little J is indicating here. And we usually write it up even if we don't mean to be a power. It's not being a power there, it's just being a label. Okay, so we have that, and then we can factor it. Okay, we can rewrite that by doing with the x and the y, the omega part, x minus I, and then the s part with a plus I. That will give us that particular expansion. But this particular way of writing it is very powerful, and that's what I want to discuss. So I'm going to, go ahead on this other screen so that we have that expansion exposed. Unfortunately, it's not doing a very good job because it dropped it into the shock tray. But maybe what I'll do is go ahead on this screen so that I can leave this thing to point at. But basically the idea is a particular one of these things, and I'm just talking about the S plus here, this elementary projection operator. This is the way to think about these angular momentum raising and lowering operators that come out if I factor this sum into a raising operator and a lowering operator times, then I have a combination of x and y frequencies with a minus sign and a plus sign so that they go together to make something that has no imaginary parts. That is what we're dealing with here. And the basic idea is that these elementary projection operators are also worth noting. That is, when I do the sum here, Sx plus I times Sy, I get, this is the Sy, this is the Sx, okay, our old friend the B, or X, and our old friend that complex C, what was called Y, in the other, outside of this room here. And that makes a projection operator that just has a 1 in the upper thing, what we call an elementary projector. It will take 2 and turn into 1, and that's all it can do. So it's a raising operator, okay? And then there are, to go with this, destructors as well. S plus is this guy in terms of the A daggers. It destroys a spin down and creates a spin up. That's a raising operator. This guy, the conjugate of it, that one destroys a spin up and creates a spin down. That's a lowering operator in our three-dimensional world. So the Z thing is just 1/2 minus 1/2. So this very easily suggests the A dagger A form for the SZ. And then all of the relations that happen are pretty easy to see. That thing that creates a spin up on the vacuum would produce a spin up vector. That's pretty easy. And then that one creates a spin down vector. 1/2 plus 1/2 and 1/2 minus 1/2 are the way those are written in this particular language here. So that's the basic idea. The raising operator here. Now, the S plus operator does two things. It destroys 1/2 and creates a plus 1/2. That's equivalent to raising 1 quantum unit. So that's why it takes 2 of the A dagger guys who are only capable of moving things by 1/2 a unit to be able to move something by a whole unit. So this is one more example of the 2-to-1 between the vector space that involves spin vectors and the oscillator space that involves A operators, a two-dimensional spin up and spin down. So once again, we're seeing the connection between the three-dimensional angular momentum vector space and the very fundamental spin a half that, well, as I've always said, we're all made out of spin a half particles. Nucleons are all spin a half, right? And then around that is orbiting electrons. They're all spin a half. Everything we own is spin a half. That's very fundamental, okay? More fundamental maybe you would like it to be, okay? So here once again is that whole idea, again, of the work that these operators do. So what we're going to be doing on Monday is we're going to be working out what this operator, these two operators, remember it takes two to tango up to 3 dimensions. That is, there are the relations again for that. And we're going to be creating boson oscillator states, but we're also going to be creating the JM states of angular momentum and working with them and getting their representations. And also right away you can see these are, in quantum mechanics books, these are at least 2 pages of derivation. Here it's 1 line. The derivation of that square root of j plus m plus 1 and j minus m. Just using our quantum numbers, which we already know you get from the formulas for creation and destruction done by 2 operators. Just substituting into that the values, j plus m and j minus m, gives you this. We're done. That's a real bugbear for the quantum mechanics books that exist now. This is so elegant. Okay, that it is really, really very important thing. The half difference, of course, I've already mentioned. Okay, that's the SZ operator. Okay. There's the L equal 1 vector. We're looking at it before, but this is what it gives. That's the formula for it right there. There's the 3 halves. Just stick in the numbers. And there's the tensor, the 5-fold dimension representation that we'll be looking at wave functions for. And I think that's it. That's the 2-dimensional oscillator right there that gives us this. Cut. We'll be taking this story further on Monday. Okay. And we didn't run out of battery yet?
No.
I think we got
really good.
I think we got a setting that works. Let's see if we got a movie. We never know what we're going to get when we play with these black boxes.